Welcome students to the next video about summarizing data in tables and graphs. Now we've already talked about qualitative data, so we're going to move into quantitative data. So in this case, the quantitative data that we're going to look at first is discrete quantitative data because it behaves similarly to qualitative data except that there is an order because numbers follow each other in an order that makes sense to us. For instance, 2 follows 1. 10 is bigger than 8. So there's already an inherent structure when we deal with quantitative data. So let's discuss some terms we're going to use. We've already talked about a frequency distribution, so that's a review. The only difference here is categories of data in the quantitative realm are known as classes. So when you see the word class, it's just a fancy way of saying category. For relative frequency, again, it's calculated the same way that it was in the previous qualitative data video. But in this case, again, we're dealing with classes instead of categories. And we are going to talk about what happens with cumulative relative frequency. Since numbers are ordered, as we collect data across different numeric values, we'll accumulate relative frequencies. And you'll see that in action as well. So let's get started with an example. So one example that I have is from this class. Thus far, the assignment completion. This is already outdated. Many of you have completed several more assignments, which I'm really excited to see. But suppose this is where the class stood at this point. So of the 28 students with 2 assignments already available to complete, here's the distribution of data. So what we're looking at here is, again, we're going to do number of assignments. We're going to list all the different categories, in this case, 0, 1, and 2. Those are going to be our classes, and these classes are individual values. Later on, we'll see intervals. And the frequency is a number of times that value shows up. If we want to calculate relative frequency, we simply divide. So for 0 assignments, the frequency was 11. If we take 11 and divide it by 28, we'll get 0.393. Similarly, if we divide 15 by 28, we'll get 0.536 for 1 assignment completed. And for 2 assignments, you see 0.071, which is 2 divided by 28. Now there's a new column called cumulative relative frequency. That one adds up the relative frequency starting at the lowest numeric value and going up to the highest numeric value. So of course, if 0 assignments, it was 0.393. That's the value that's going to be for the cumulative relative frequency. Only after we add an additional number, so the 1 assignment category, do we add the 0.536. So when you add 0.393 and 0.536, that's where the 0.929 value is coming from. And of course, if you add up all the relative frequencies, you should get 1. Now, let's look at the graphical display for the frequency. So the difference here is because numbers come in order, and they are in fact touching, right? When we had categories such as the Bronx and Manhattan, those are locations and they're not necessarily adjacent to each other. So having the bars touch, we do not do for categorical data because there's no connection. Numbers, on the other hand, are connected. So 0 and 1 and 2 in this situation are touching. When the bar graph is touching, it's known as a histogram. And histograms are used for numeric data. In this case, for discrete, the value is centered for each of the bars, and the bars are touching. We'll go more into developing histograms and determining bins in a moment. Another way we can quickly organize data that's discrete is through a stem and leaf plot. Now here, this example consists of basketball scores for both the men's and the women's basketball team in 2017. So looking at this data, what we're trying to do is determine which team is more successful in 2017. So one way to go about doing that is to actually create a histogram with bins that are size 10. That'll make more sense soon when we discuss how to create such bins, but a stem and leaf plot automatically does this. So a stem and leaf plot consists of two pieces of the numeric value. On the right-hand side is known as the leaf, and this is the last digit of any of the values above. So when we talk about 63 as one of the data values, the last digit in that number is 3, so it goes on the right side. Only one digit for each of the data values goes on the right side. When you look at the 8 row, where you have values such as 88, 88, 85, and 86, you see those in the stem and leaf plot, where each of those 80s ends in different values. So on the right-hand side, next to the 8, on the left, you'll see a 5, a 6, an 8, and an 8. So those represent the 4 data values in the 80s. On the left-hand side is the stem, which consists of all the remaining digits at the start of the number, not the last digit. So whatever comes before will go on the left-hand side. This is really important when you look at a value like 101. So it's represented as a 10 for a stem and a 1 for a leaf. I'm going to pause here and give you a moment to try to see if this makes sense to you. So here again, we have a stem and leaf plot. This one's for the women's scores. And the same holds true for the stem and leaf. Now, what's interesting about stem plots is that you can compare them side by side. So here we're trying to compare the men's scores and the women's scores for the same year in basketball. On the left, you can see the men's stem and leaf plot that we created, but now it's on the left-hand side. So again, we still have 63 as one of their scores, but now we've reversed it because we put all of the stems in the middle, and the leaves for the men is on the left and the leaves for the women is on the right. So that might be a little confusing, but this is how to do a side-by-side stem and leaf plot. If it doesn't look familiar, go back and look at the men's score and see how it's on the left-hand side now. And the women's score is now on the right. But still, the stems are the center column. The 6, 7, 8, 9, 10, 11 are the starting digits for all of the data values. And on either side are the leaves. And you'll know these are leaves because you can actually turn your head sideways for both, and you sort of see a little histogram. So if you turn sideways, you can see the men's histogram and the women's histogram. And from this, you can see that actually the women have higher scores, especially in the 90s. They have a lot more 90 scores and the same number of 100 scores, and then 110 through 120, they have the same. So overall, the women's leans more towards the higher end of scores, so they actually performed better. I'll take you a moment to think about that. It's a little confusing, but that's the interpretation of this data. All right, so now we're going to talk about how to make a histogram. So we have values that touch, and that's fine when you have single values or you break it down by 10. But what if you want different bars and different widths for those bars? So I'm going to pause here again, and I'm going to give you a chance to try to fill in what are the missing values that I didn't write on these number lines that exist based on the dashes. If you haven't had enough time to think about this, please pause the video and take more time. Okay, now that you're back with us, let's look at each of these. Now, there is a magic formula that comes from statistics, and it is called the class width, where you take the largest value on the number line or for the data, minus the smallest value, and you divide by number of classes. Again, classes are the categories. In this case, it's the spaces in between those dashed lines. So let's peel back the layers here and look at what we're really dealing with. If we go from 0 to 24, that is a distance of 24. And that would be subtracting the maximum and minimum in this case. Now, if we look at the classes, there's one class right there. Now, how many classes do we have? Well, if we point to all of the spaces, we have a total of 12 classes, right? You can see it there, 2, 4, 6, 8, 10, 12 classes. So using this formula, it's simply a matter of 24 minus 0, which we know is a distance of 24, and dividing by those 12 spaces that we want, we'll end up with a class width of 2. So you might have noticed here that we're counting by 2s. So it goes from 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, let's move on to the next one. The more examples you see, the more it'll make sense. The other example I gave you was this one. Again, feel free to pause the video here, and I'll meet back with you on the other side. Okay, now that you've had a moment to think about it, the game is still the same. We try to figure out the distance between the minimum and maximum, and in this case, that's 20 minus 0, which gives us 20. Again, we're looking at the number of classes. There's one class. They're much wider, so we already know the class width is going to be bigger. And in fact, there are 4 classes that we have divided this one into. So we use our handy formula again. We know that 20 minus 0 again is 20, and we have 4 classes, so we're going to divide by 4, and that gives us a class width of 5, which means going from one tick mark to the next, we'll be counting by 5s. So it goes 0, 5, 10, 15, 20. Okay, let's do our last example. So in this last example, I threw a curveball. The maximum and minimum are no longer a high value and 0. There are actually 2 values here, but the game is still the same. For this distance, we have 27 minus 12, which gives us a span of 15. Now we have our class, this one space. There are a total of 5 such spaces. So using the handy dandy formula, again, we have 27 minus 12, which gives us our 15. We divide by 5 and we get 3. Now in statistics, the game of maximum minus minimum divided by the number of groups we want, the classes, may not always come out to a whole number. If you end up with a decimal, the best thing to do is round up, because that makes it wider and guarantees that all the data will fall within that. If you round down, you're going to miss your maximum value every time. So if you end up with a class width that is a decimal, it's usually easy to not deal with decimals. So my recommendation would be to round up. Again, this is a way to look at data. It isn't a way to be exact about the data, right? We're organizing it in a way that makes sense to us. And there are various ways to organize data. That's actually one of the tricky parts of statistics and makes it easy to lie with statistics. So be warned, some of these tools can be used in ways that are less than ethical. We're going to walk through one more example. And for this one, we are going to change the class width 3 times to see what happens to the distribution and what it looks like when we do that each of those times. So we're going to start out with just looking at the data first. So this data is about the waiting time for individuals waiting trial at 40 different precincts in the city. Now, this is a fictitious problem. It's adapted from another problem, but there is this aspect of waiting that occurs before trials. So there may be data out there that you could use in reality, but again, this is fictitious. So suppose these are the waiting times for the individuals awaiting trial, and these will be in minutes. Now we can play the game that we played before where we try to organize it. We're going to create some relative frequencies in classes and then try to get a visualization of the data. I keep putting this up here so that we know what relative frequency is. It's really an important concept, and that's why you'll see it over and over again, even in this video. So here, let's make a frequency table. We have the number of people waiting. So here we have all of the different values that appear in the data and the frequencies of them as well. Oh, I apologize. It's not in minutes. It's the number of people waiting. Now, when we look at it, we also have the relative frequency. Again, the relative frequency is the frequency. So in this case, the very first one for 3 people waiting is 2 divided by 40, and that gives you 0.050. And so on and so forth. If you want to do all these calculations, it's good practice. But again, that is relative frequency. So we are going to look at a histogram. Now, when you only have a single group that you're looking at, you'll find that the frequency and relative frequency histograms look very, very similar. In fact, identical, except for the vertical axis. So in this case, you can use whichever you want. I always gravitate towards relative frequency because it has so much more information. But again, we're learning, so either one at this stage is fine. So let's use frequency just for simplicity's sake. And let's say we're going to come up with some classes and we're going to create intervals. So instead of having a single value like 3, 4, 5, 6, we're going to actually create an interval of values. We're going to have a lower limit and we're going to have an upper limit that creates that interval. And we create these intervals by the method that we used when we were figuring out the missing values for the number line. And that will help us figure out the class width. So in this case, suppose we want a class width that goes from 0 to 2. So each of these have a class width of 3, has the values 0, 1, and 2. And we can count the frequencies within those intervals. So 0, 1, and 2 had no one. The values actually began at 3. So 3 to 5 had 8. If you add those up, you'll see 2 plus 3 plus 3 is 8. From 6 through 8, you have 17. 9 through 11, you have 12. And then 12 through 14, you have 3. So now we've condensed the number of people waiting into intervals to get a more useful picture. So now we've gone from the histogram on the left to the histogram on the right. We've gained generality. So now we know where more individuals lie in terms of the intervals, but we've lost the specifics. So there's a trade-off that happens here. But in this case, we can say that the most common number of people waiting trial is between 6 and 9, because that's the tallest bar. Before it was just 8 seemed to be the highest, but we didn't know if that was an anomaly or if there's a span of time to the left or right of it that's more likely. Or I'm sorry, the span of number of people left or right of it was more likely. So we might gain a little bit more in generality. Just for practice, let's do it again. We're going to collapse the interval even further. Now we're going to have an interval of 0, 1, 2, 3, and 4. So now the class width is 5. There are 5 values there. And by condensing it in this way, we have from 0 to 4, we have 5 values. From 5 to 9, we have 24. And from 10 to 14, we have 11. So as we play with the bins, we see different outcomes in terms of the histogram. So what we choose for the class width and the starting values really impacts what we get for our visual. These are all mathematically correct, but some might be more appropriate and useful for interpretation than others. And that's the tricky part about statistics. The mathematics is straightforward. We've just added values and frequencies and counts, but the interpretation becomes critical. Now, I've provided 2 more practice problems for you to go over in the PowerPoint. I'll go over them really quickly here, but take your time doing it. So here I just came up with, again, the classes. And in this case, I went from 20 to 30. So each of the class widths is a span of 10. And when you see numbers such as 20 to 30 and then 30 to 40, one question might be, well, which one of these rows actually has the 30? And general practice is that the lower class limit, the number on the left, is where the value would land. So just to clarify it, when we have 20 to 30 in this case, and you look up at the data, you see 29 and 30. The 29 goes in the first row. The 30 actually is counted in the second row because it picks up at 30 and starts counting there again. What would be ideal is have this say 20 to 29.9999999, but that's just complicated to write. So we just put the value and know that the lower limit is where that bin starts and where the count would start. I hope that was helpful. And that is it for discrete data. So the new thing that we learned is histograms and the class width that dictates what histograms look like. I will see you in the next video. It will be on continuous data, and it will be the same game, but the values for the data will have decimals. Otherwise, the whole process is exactly the same. I'll see you at that video soon.